Hey y'all, how you doing? Hope you're having a good day. Today, we're going to continue the discussion on the time evolution of the density matrix. And we're going to make a quantum leap from Hilbert space to Louisville space. So Hilbert space is a space you normally work in quantum mechanics, where you consider pure states, which you can write as a vector or wave function. And Louisville space, you don't consider wave functions, you consider density matrices. And it's sort of one dimension above the Hilbert space. So, to start off, we're going to consider a two-state system. And we're going to call our two states state 1 and state 2. And we're going to say that they have a Hamiltonian that doesn't depend on time. And the most general way to write the Hamiltonian of a two-state system is to just write out each element explicitly. So the subscripts are going to denote, the first subscript denotes the row, the second subscript denotes the column. So for instance, this element here is the Hamiltonian element that's in the first row, second column. But we're going to say that state 1 has an energy of E1, state 2 has an energy of E2, and these states are coupled by a certain coupling constant. So here we're going to say that H11 is equal to E1, H22 is equal to E2, and they're coupled by this constant I'm going to call V. And we'll keep the subscripts on it, because V12 is not necessarily equal to V21. And so this whole matrix consists of constants. Nothing depends on time here, because I said our Hamiltonian is going to be time independent. But we're going to write things in terms of this at first. That way it's easy to generalize in case we want to change our Hamiltonian to be time dependent. So now we're thinking about a two-state system with these states in this Hamiltonian. And we know that a general density matrix, we're going to consider it depending on time, and general density matrix you can just write like this. Okay, and each element depends on time. I'm just not writing it explicitly. So now, the Liouville equation says the time derivative of the density function is equal to negative I over h bar times the Liouville operator times the density matrix. And I discussed in a previous video that the Liouville operator is just a commutator with the Hamiltonian in the first slot and whatever you're operating on in the second slot. So here we're operating on the density matrix, so we're going to put that in the second slot. And what we're going to do here in this video is we're going to solve, in terms of the elements, this equation right here. So, remember that the commutator between h and rho is just h times rho minus rho times h. And since they're matrices, these products are not always the same, like they are with numbers, because whereas numbers always commute, matrices do not always commute. So we're going to use these matrices up here, solve for this. So that's going to be the first part of our strategy. And now the second part of our strategy, well, the first part is going to be do these parts individually. And then the next part of our strategy, it's going to be a big matrix. Well, I mean, it's only 2 by 2, but each element's going to be, basically a whole equation. So we're going to write out this, and then we're going to equate the left side of the Liouville equation with, which is a 2 by 2 matrix, with its respective element in the right side. So here I'm going to start out by multiplying our Hamiltonian, which we called h, with the superscript 0, And note that that's not an exponent, that's just a superscript. Just notation. Okay, so I'm going to perform these matrix multiplications, and then I'll talk after that. Okay, so that's what we get for our commutator. Now this is completely general. Any 2 by 2 matrix, if you take the difference between them, or if you take the commutator between them, you're going to end up getting something like this, depending on what you call your elements. And although this is much easier to do with a computer, I think it's helpful just to see it written out explicitly, just so you know that I'm not doing any magic tricks. I'm doing matrix multiplication here, which just has simple rules, which got us to here. And now is an important part where I'm going to, since we know that the elements of our Hamiltonian are just constants, which we wrote up here as these elements, so I'm going to exchange all the h whatevers with what's here. And by doing that, I can, let's take this term for instance, by doing that, I can bring this out front of the density matrix element, and then things will cancel, and also other things will be able to be grouped together. So that'll clean things up. So let's do that now. Okay, all I did there was bring the constant out front of the density matrix elements. That's allowed. And now what I'm going to do is group certain terms together and cancel certain terms. Well, we can see what terms are going to cancel here. So this term is going to cancel with this term. And this term is going to cancel with this term. So saw that. And now we have a, let's see here. Okay, that's going to stay like that. We have a row 1, 2 here, so I'm going to group that. And we have a V12 here. And we have something similar down here. So I'll write that on the next page now. Okay, so that's our commutator, and that was the hardest part, math-wise, that we have to do. So let's just rewrite the Liouville equation, just to keep in mind what it looks like. So that's what our equation looks like. And now, remember I wrote row element-wise on the previous page, and now we have this. So let's plug both of them in. And we're going to obtain 4 equations, and I'm going to rewrite the left-hand side like this, so write it out element-wise, and then I'm just going to put the dot over each of the p's, so I'm essentially absorbing the differential operator inside the matrix, and I'm kind of changing the notation. So for example, row 1, 1, dot, which is ddt row 1, 1, is, it depends on time, but I won't write that either, is equal to negative I over h bar times the first element in this commutator. So times v12 row 2, 1 minus v21 row 1, 2. And to make it easier, I'll actually write this whole thing out. So you see that all I'm doing is equating the elements on the left-hand side with the elements on the right-hand side. Okay, so there's our set of 4 equations. And now, here is a very important part. We can represent this set of 4 equations as, well, we can represent the left side as a matrix. Not a matrix. We can represent it as a vector instead of a matrix. And we can write that that vector is equal to some matrix times another vector, where the other vector is going to be these row elements. So we're basically going to write this stack of things as a vector. And then we're going to write all the rows. So all the rows are going to come together and form another vector, which is different from this vector, because this vector is the time derivative of the rows. And then all the other stuff, once the rows are out of it, is going to be the matrix. And it will be much clearer when I write it out. So all I did was write this set of 4 differential equations in matrix form. I haven't broken any rules here. I'm just changing the representation. And you can see that if you perform this matrix multiplication. You see that row, well, the time derivative of row 1, 1 is equal to 0 times row 1, 1, because there's no row 1, 1 in the first equation here, plus, well, there's a negative I over h bar out here, which I forgot to write. So, plus negative v21 times rho 12, which is this second term in the first equation here, and then plus v21 times rho 21, which is the first term in this equation, and then 0 times rho 22, because rho 22 does not appear in the first equation. And I did that for the same things. And now this matrix kind of looks ugly. We can rewrite it because, I mean, we could have changed the order we wrote these equations. It doesn't matter. They're still the same equations. So instead of writing them in this order, I'm going to write rho 1, 1, rho 2, 2, rho 1, 2, and rho 2, 1. And by writing it this way, this matrix looks a lot prettier. Okay, so there we go. It looks a lot prettier. And all I did was basically shift the rows up or down, like the whole row. So I took row 2, 2, and I just moved it up here. I mean, that's really the only thing I did, I think. Okay, yeah, and that sort of changes these columns around. If you do the matrix multiplication, you will see it's the same as these 4 equations. So, you should find that really fascinating, because this matrix, it looks like a larger matrix of 4 smaller matrices, because you see this 2 by 2 matrix in the corner here is just the 0 matrix. This matrix here is like some sort of coupling matrix. This matrix here is also like a different sort of coupling matrix. And this matrix down here is just a difference of the energies. So, what we just did there was we made a leap from Hilbert space representation to Louisville space representation. And so it's the same math, same physics going on here. It's just different representation. It's like if you want to represent a set of equations by just writing them out versus writing them in vector form. So this matrix here, the name we give it is the Liouville operator. And now, notice, let me go on to the next page here. Notice that we started with a two-state system. In general, you can start with an n-state system. Let's do it this way. Our case, and then the general case. So in our case, it's a two-state system. General case, n states. And in our case, our Hamiltonian was a 2x2 matrix. And so was rho. So rho and the Hamiltonian is 2x2 matrix. The general case, rho and the Hamiltonian, is an n by n matrix. And by going through what we just did, we found that we have a new matrix. And this new matrix is the Liouville operator. It's a 4x4 matrix. So what that effectively did was square both of these. We squared 2 and we squared 2 here. So, in general, the Liouville operator is an n squared by an n squared matrix. So you can see why I only did it for the two-state case, because anything else, and you're going to want to use a computer. So, like I said, this new matrix called the Liouville operator. And we jumped from Hilbert space to Louisville space. And notice one other thing, that matrices in Hilbert space are represented as vectors in Louisville space. So I'll write that down. Matrices in Hilbert space are vectors in Louisville space. So it's almost like we squished things down a dimension, but we kept the same amount of information. But notice, matrices in Louisville space, they have no analog in Hilbert space. So if you go from Louisville space back to Hilbert space, well, you lose information that's contained in, for instance, this Louisville matrix. So for instance, there might be information in this little submatrix here that you're going to lose if you try to transform from Louisville back to Hilbert space. So matrices in Louisville space have no analog in Hilbert space. So, I hope you enjoyed that quantum leap from Hilbert space to Louisville space. And things are much more general in Louisville space, and they contain the same amount of information as in Hilbert space. Sometimes it's not always easier to work with Louisville space, though, because it's unfamiliar to a lot of people. So I hope you enjoyed that video. If you liked it, give me a thumbs up. If you didn't, give me a thumbs down. I'll be making another video about Louisville space and how, in the comparison between Hilbert space and Louisville space. And that should clear more of your questions up, hopefully. So once again, thanks for watching, and have a great day.